So, you are building something called LM26. Tell us about LM26.
All right. So at General Fusion, we want to do something magnetized target fusion, which is something of a mix between the laser fusion and the magnetic fusion. We have a big bucket of liquid and we compress plasma with that thing. It has a lot of advantage for a power plant. But we do need to show that at the middle, we make the fusion happening. So LM26 is a watered-down version of that, a prototype, which will compress the plasma over the next couple of years. And the machine is built, actually. We built it. We got our first plasma about a month ago. We will start compressing plasma in that machine in about a month or two. The first thing we want to achieve is showing that it heats up. The plasma, when we make it, is about like 100 million degrees C. We first want to compress it to 10 million degrees C, about this summer or something. And then next year, we will compress to 100 million degrees C, which is the temperature required for fusion. And then after that, we will add some density. And we want to compress it all the way to the Lawson criteria at the end of 2026. Therefore, Lawson Machine 26. That's where the name comes from.
And so I think people may take a little bit of time getting their head around this. You are just crushing things with metal.
Yes.
How do you do that? With pistons? With explosives?
With pistons. Yeah, well, we have tried explosive in the past as tests. We have done some small tests of plasma about this big. We squash it with explosive. We saw that the neutron count coming out of this thing shot up. But that was a small test. But in a real power plant, we want to repeat that every second. So explosive is not a done thing. So we want to have a big bucket, 4 meters in diameter, spin it. The centrifugal force push the liquid lithium on the wall. Then there's a whole bunch of piston around, a bit like syringe. And the steam pressure pushed on the piston, compress the lithium, and then the lithium compress the plasma. And at peak compression, you have a big flash of neutrons, and the neutrons get all absorbed by the liquid metal. Lots of the other people will have a big problem with their metal being destroyed by the neutron. We have here people talking about material science and everything. Well, we fix that problem. We have that today. We don't have to wait for invented a new material or nothing. The liquid metal will absorb that. We have a big tritium breeding ratio because we have so much liquid in there. We catch all the neutron, and we have a breeding ratio of 1.5 with natural lithium, not even lithium-6. So that's another advantage. It's cheap because we don't have superconducting coil, we don't have laser, we don't have neutral beam, RF heating, none of that thing. So this is very good for a power plant.
And where does the magnetic bit of it come in?
When we inject the plasma, we have a bit of a coil there, a copper coil, nothing very high. And then when the plasma is formed, it shoots through that, it wraps itself around the magnetic field, and it makes a twisty, windy magnet of the correct geometry to keep the plasma in shape.
Twisty and windy.
Yes.
Yeah,
But actually, the real magnetic configuration, it's a bit confusing. The magnetic configuration that we have is the same as a spherical tokamak, but we don't form it the same way.
Right. And what's the heritage for systems that use liquid lithium as a working fluid as well as a neutron absorber?
Well, there's a few fission reactors that have worked in liquid sodium, for example, as a neutron and a heat machine to take the heat out. And actually, this idea is not from General Fusion. That was proposed by the Naval Research Lab in the 70s, a concept called Linus. They worked a bit on this in the 70s, but then they abandoned that. And when I was designing General Fusion, I look at all those other ways of doing fusion, and I say, hey, this is a good method because it would be excellent for the power plant. It fixes a lot of the power plant issues.
And do you sometimes worry about the fact that you're pursuing this somewhat on your own?
Well, on my own. There's 130 people in the company.
No. As a company.
I'm not the only guy in the last ranch here.
No, but other people looking at ways of doing this have not gone this down.
Yes, there's not too many people doing that. There's a few other companies out there that are investigating a thick liquid wall facing the plasma, which I think actually is a very good idea because this will protect from the neutron. But none of them are doing the compression the way we're doing. So we're a bit independent, and that's actually an advantage, in my opinion. Everybody wants to make a tokamak, and it's not a good idea. So we have a good idea.
Okay. The question of whether a tokamak is a good idea can be raised at a
yes, that could be discussed endlessly.
But the thing that given that fusion is not being regulated in the same way as fission in at least some places, how big an advantage is not having to worry about neutron embrittlement of the wall of the...
I think it's one of the key advantage of our system because people will have to invent a new material. And new material takes a long time to build, right? So like in Spain, they're building a machine that will take 10 years to build just to test material. So, when will the material be ready? But we don't need that.
But you do have because you mentioned liquid sodium reactor.
No, all is liquid lithium.
No, I know you're using liquid lithium, but I'm just asking, liquid sodium does have corrosion issues. Are there corrosion issues with the liquid lithium?
Yeah, there's corrosion issue, yes.
And you're happy that you've...
Well, there's some literature about people that have, run liquid lithium on piece of metal, and stainless steel 316 corrode at so many micron per year, and it's good. But it's, you have to be a bit careful what you put in there, right?
Right. And then, is there any advantage with working with a hot or intermediate fluid?
Well, it's good to extract the energy. Like we're going to pump this lithium out, hit the boiler, make some steam. The steam spin the turbine, and some of the steam push on the piston. Like a lot of fusion concept, you need recirculated energy. And we recirculate the energy, the steam from the boiler, push on the piston. Like a laser, they will have to make electricity, charge capacitor, fire some flash lamp, and you lose at each step, and it costs at each step. But our system, we push straight on the piston with the steam, so it's very direct.
Does that also mean that you're less tied into a complex fusion-specific supply chain issue?
The supply chain issue. So,
speaking as a Canadian,
we hear a lot about the supply issue. Everybody is very... However, my supply issue is I'm doing piston with cylinder, with bearing, with steel that anybody can do. Like at General Fusion, we design our machine and the local machine shop make it for us. Like we don't need special superconductor made in Japan. We don't need special laser made. I don't know where the lasers are made, but we need some piston, some metal, and that can be machined locally. So it's much simpler to manufacture. It's much cheaper, and when we do a power plant, it will make a smaller cost of electricity.
How big a power plant would you be thinking of making?
Well, we try to make the power plant as small as possible. Now, fusion works better bigger. A big blob of plasma stay hot longer than a smaller. So the smallest one that we currently can make electricity at an economical plant is about 150 megawatt electric. Now, we could do bigger. It would actually be more efficient, but a bigger machine costs more money to make, takes longer to develop, and it's more difficult to make bigger machines. So we're trying to make it as small as possible. And 150 megawatt electric.
And what sort of cycle frequency is that?
150 megawatt is the DC electricity coming out. But the cycle that we want to do is 1 time per second. So we go 1 time per second. But because of the thermal inertia of the fluid, the turbine will spin continuously and pick out 150 megawatt electric.
And so but it will spin continuously, but at different speeds, because presumably when it compresses, it picks up angular momentum.
The boiler boils some steam all the time, and the steam spins the turbine all the time. So this is continuous. It's not pulse. But some of the steam come with a valve to go on the piston and push it inwards, and that will be pulse with the valve that go click, 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 and fire the thing.
Okay, click, 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 click.
Yeah.
Okay.
Cronk, maybe.
So you've been, how long did you start General Fusion with this technology in mind?
Yes, I did.
Yeah.
Well, no, that's not totally true, actually. So I left my good paying job and I started General Fusion with 0 salary. My wife didn't like that very much. But
you tell her about the romance of fusion and powering the stars.
No, this fusion's not good for romance, I think. Don't go in fusion for catching girls. Not a good idea. Where was I? Oh, yeah. So I didn't know that I would take that technique. I knew I didn't want to do the laser and the tokamak because I think they're bad ideas, but I didn't know exactly which technique to use. So I lie on the sofa, I read all the literature, and then I went through this Naval Research Lab Linus thing, and I said, now this is a good idea. So I picked that up at that time. And ever since General Fusion, we have hit some technical problem and modify in detail, but the basic idea have remained the same since the beginning of General Fusion.
And do you work a lot with national laboratories in the States as well as in Canada?
We have a bunch of little, cooperation with various labs. Like in the state, we have some people doing some plasma analysis at Princeton to make sure the plasma stays stable, the windy magnetic field is just right. We talk with UKAA people. They're helping us actually on diagnostic and neutron counting and this sort of thing. So we have collaboration with various people. McGill in Canada is calculating some fluid-liquid implosion. So we have people here and there working on a small contract that we fired out.
And from LM26, what's the pathway? What are the milestones between that and a commercial reactor?
All right. So LM26 we'll do 1 kV this year, 10 kV next year, and break even end of 2026. And after that, we want to make the near commercial machine, which will be a bigger machine, 4 meters diameter, with piston and swirling liquid metal, and hopefully tritium. We had some arrangement to do that at UKA site in Column. So this is likely where it's going to go, but it's in the future, so that could change. But that was the plan initially. This will fire not at 1 hertz, though it will fire at lower repetition rate. But this, we want engineering break-even in this one. We stick a thermometer in the liquid, we fire 1 shot, and the thermal energy is enough to run the power plant and get on, but on a low rep rate.
Right.
And then that will be ready in like 2030 or so. And then in 2035, we want to increase the rep rate at 1 time per second and stick the turbine on the backside and make electricity for the first time in 2035.
Okay.
Yes.
Any questions for Michel? Yes.
Talk a little bit about the magnetic field configuration inside the device. Is it
All right.
field reverse configuration?
No,
Is it
no,
a straight data
no,
pitch?
it's a spherical tokamak. So what we have a shaft in the center, and then the liquid on the outside, and then we pass millions of amp in the shaft that makes the toroidal field, and there's what we call a stuffing flux into the gun that comes out, and when the magnetic field just wrap itself around and settle down, we have a spherical tokamak magnetic configuration, which have the advantage that we can use 30 years worth of tokamak data to calculate what our confinement will be and all those things.
And you've shown that at the experiments at Princeton that you're
Princeton is calculating the stability, like as you compress, the shape change and everything. And Princeton is calculating that we don't hit instability in the plasma during the compression. But we formed those things, like the 2-meter machine right now produce plasma, and they last the energy confinement time is 10 milliseconds, and we want to compress it in 2 to 3 milliseconds. So we're good. Like it lasts longer than the compression time, which is an important factor for us.
Absolutely, yes. Otherwise, yes, you're a little lost.
In case of
Another question there. You have to wait for the microphone because the nice people who are listening.
What material withstands a heat at 100 million degrees Celsius?
All right, no material can withstand 100 million degrees C. You have magnetic field. The plasma at 100 million degrees C is stuck in the magnetic field, and then there's a bunch of magnetic field, and then there's the wall that's sitting at like 200 degrees C or something. So there's no material that really go to 100 million degrees C in this thing. It's the same as a tokamak. Any magnetic confined system, the magnetic field isolate the plasma from the wall. So the wall does not touch the plasma. Otherwise, that wouldn't work. 100 million degrees C will kill anything.
But during the collapse, at some point, surely the wall comes within the magnetic field.
No, because it's the liquid is a conductor.
Right.
So when it comes in, it actually compresses the magnetic field. So a lot of people think that we push on the plasma with the wall. Incorrect. We have magnetic field with plasma in it, and when the liner come in, it pushes the magnetic field in front of it. Like if it would be a superconductor, the magnetic field will not penetrate at all. Now, because unfortunately it is a conductor, we lose a bit of flux, but we lose only about 5 to 10% of the flux diffused in the metal, but the rest is compressed. So you don't push on the plasma, otherwise it would cool down.
Right. Yes.
Sorry, just to confirm, did you say 2035 and 150 megawatts? And how much investment is needed to create this plant?
Number one. Yes, I said 2035. Approximative amount of investment, but we don't really know the exact number. Probably 2 billion to get there. From here to there, 2 billion.
And how much money have you raised so far?
300 million. About a quarter of that is from the government of Canada, and the rest is investor from here, there, and everywhere. But yeah, you need some money to make those things, unfortunately.
Great. Well, Michel, thank you very much indeed. And thanks for getting us off to start with our
Thank you.
milestones and markets.